we learned about graph last Monday, and I would like to let you know how we can implement the graph, how can we make the code. So actually there are some codes, there are some libraries that you can use to deal with the graph. But now let me just give you the very basic ADT, the very basic abstract data type. And yeah, if you later use a kind of library in Python, yeah, there is another library in Python, we call it the MX network. Yeah. So the basic idea will be similar with this kind of ADD. So for example, you already know the class graph, and in the class graph we can create another class. So in this case we have the vertex, and then we have also heads. So inside the class there will be another class, and as we already learned in the PowerPoint, we know that each of the vertex can have element. In the case of our example, we know the element represent the airport airport code. So like the Honolulu or San Francisco and etc. And then we need to make a constructor. So this is a constructor. And then we can define the element. It means I want to know what is the element. And then yeah, if you want to make a map and then you want to put the vertex in a map, you can define the hash. After you have the vertex, we want to make the edges. So the edges contain three kind of attributes: origin, destination, and element. So we can construct the edges u, v, and x. U is the origin, and v is the destination, and x is the element. So we assign each of these attribute to the variable. U is the origin, and then v is the destination, and x is the element. We can call the endpoints. So the endpoint means the origin and the destination. So the origin and the destination. The opposite of v is, we know, if we are having an object of x, so the opposite of v will be u. And yeah, we need to check if it is not the instance, then we will give the error message. V must be a vertex. So we will check if V is an instance of the graph vertex or not. If it is an instance of the vertex, then let's check the destination. So if V is the origin, yeah, we need to check the destination. If it is not origin, then V will be the destination. Okay, so it can be either of origin or destination. If you cannot find any of the destination or origin, then V is not incident to X. So there are three possibilities. V is not the instance, or V is not incident to that X, or yeah, we can make what is the destination or what is the origin. So we can return the element, and then we can put the X, we can put the X into a kind of hash. So it is to map into the key of the dictionary, and then yeah, we just want to show the X. So those two classes are related with the vertex and X, and now we are going to create the graph. So the graph itself, we want to construct, as you might know, that the graph can have directed and undirected. So if we specify false, it means undirected, and the default will be false. And then we define two kind of ads: outgoing and incoming. It is to indicate that if we have V, then we can say this is outgoing. If there is an ads coming to V, then because this is incoming. Okay, so the upper side is the outgoing and the below side is incoming. So that's the meaning by incoming and outgoing. And then after we define this one, we want to validate the vertex, whether the vertex is an instance of self vertex or not. And then we want to know whether this V is in the outgoing or not. So it is to check whether the vertex is in the graph or sorry, vertex does not belong to this graph if it is not in the outgoing, and then the vertex is an instance of vertex or not. And then we want to check if it is a directed graph or not. So we will check about the incoming and the outgoing. We want to know how many vertex, so we can just call length. And then if I want to know the vertices, it means I want to know all the keys, because we are using the dictionary, so we can just call the key. And then if I want to know the count, how many ads count, so if it is directed, then we can just call total. If it is not directed, then we can divide by 2. If we have the edges, okay, we also want to see the values for every of the outgoing. And then if we want to get the edge, we can first validate U, whether it is exists or not. We want to validate the V, whether the V exists or not. And then we can get the V. And then if I want to know the degree, so the degree of V, I can just return the length of the ADG. It means this is the adjacent edges. If the edges are adjacent in the outgoing, then we can look at how many edges in this particular V. So incident edges, we want to know what is the edges. I think you already know also this is it is related also to this adjacent. Okay, so we want to know all the possible incident edges. So the idea is the same. We want to check the outgoing and the incoming. And then if we want to insert, then we need to make an object into the vertex, and then we will make an outgoing as a dictionary, and then we will check if it is directed or not. If it is not directed, then if it is undirected, then we can just have the ends. But if it is directed, then we need to specify the incoming. And then for the inserted x, it's also the same. When we have the vertex, we can insert the x. So the x will be determined by the u and v. And let's make the x equal to none, because this is the basic, the default. And let's check if the x exists or not. So if it is already exists, then u and v are already adjacent, so we don't need to add that x. If it does not exist, then we will make the x, and then we determine the outgoing and we determine the incoming. Okay, so this is the basic ADT, okay, as I mentioned to you. Maybe in the later part, I will use some of the existing library, because nowadays there are many libraries in Python that you can use to make this kind of graph. If you want to build from the scratch like this one, that's also fine, because you need to know what kind of methods that you can use. That's why I show this one. Now let's see how if we want to make the graph. And as you know, we have several structures for the graph. Do you still remember? We have edge list, we have adjacent list, and then we have adjacency matrix. Okay. Now let's look at the edge list. How we can develop the edge list. Let's suppose I have this simple example of the graph. Okay, I show you the graph example in a separate PowerPoint. You can get in the e-class. Okay. So I just upload the file. Now let's see, I have this kind of transportation network in Korea, but yeah, let's just consider this one. Node represent the city, and then X represent the availability of the transport. Maybe yeah, you want to make a kind of delivery system from Seoul to any of the cities, but you have limited trucks or you have limited vehicles. So you design that from Seoul you can deliver some products to Daejeon, and then from Daejeon you can deliver some products to Busan. From Busan you can deliver products to Daejeon. But before you visit Seoul, yeah, from Daejeon you need to visit Suwon and then go to Seoul. And from Seoul, you can go to Gwangju. And from Gwangju, if you want to return back to Seoul, let's visit Suwon. So yeah, this kind of network. Let's try to make it into the graph. So this is the graph with the edge list. Okay. Do you still remember edge list? What is edge list? In the edge list, so we have E. What is E? It is the edge to represent that it is a combination of U and P. Okay. U and P. Then we will build the code as U and P. So this is one edge. This is another U and P. So this is another edge. This is another U and P. And so on. So for every edge, we will need to divide in E. So I make one function, then the function is simple example. And then after I have this one, I want to put it into the graph from edge list. Okay. And the graph from edge list is this one. Let's make the E, and then let's assume that the directed is false. So it means undirected graph. If it is undirected graph, so I would like to make the graph, and the graph, the directed is false, then it is undirected. So let's be the set, and then I would like to add for the V as the E0, and then I want to add E1 in the V. So you can follow this one. This is a dictionary, and then we want to find for every V, if it is a new, then you can just insert for every V into the dictionary, and then for every E, we want to also insert it. So I have another example. This is an example from the book. Okay, so this is an example from the book. This is a graph of a network of airport in the United States. So node represent the airport code, and X represent the route or the trip of the airplane. And let's say now we have no elements or we have no properties. So SFO is the San Francisco, and then LAX is Los Angeles, and etc. And if you look at this one, there is a direction. Okay, and oh, so this one is true. Sorry, this is true. Okay, sorry, I thought this is the, yeah, because it is true. Okay, so the directive becomes true, so this is also true. Okay, and yeah, this is the X list. So I define for every of the airport code. Let's say this is Boston to San Francisco, and then Boston to JFK, Boston to Miami, and so on. And it depends on the graph network. So this is the graph network. You can see Boston to SFO, Boston to JFK, Boston to Miami. So you need to define each of these X into the graph. So let's see if I run this code. Now I can make one object or one variable as the instance of simple example. From the simple example, I know this graph is a kind of object, and inside of the object we can get all the attributes. For example, I want to know the incoming. So if you want to check, the graph actually is an object. Okay, so it is an object of a graph. So this is the graph. Okay, this is the class graph, and then when you construct the graph at the first time, you will have the attributes outgoing and incoming. And then I would like to know what is the incoming, for example. Okay, so I want to just get the incoming. Yeah, you can check if it is the incoming. Actually, it is also a kind of object. Okay, so inside of this object, you want to put it into a dictionary, and we can put it into the variable incoming. Yeah, if you look at this incoming, it is another object. Okay, you cannot open it, and if you want to open it, you can try to figure out that it is a dictionary, so you can make a loop, and this is a loop, and you want to know what is the key and what is the value from this incoming. After I know the key and the value, so I want to check for every element of the key. After I know the element of the key, so I want to check what is every item of the V or the value. If you do this one, then you will see that this is for the incoming. The incoming, it means from Busan, there is an incoming at Daejeon. In the Daejeon, there is an incoming at of Seoul and Busan. For Suwon, there is an incoming at Daejeon and Gwangju, and so on. Okay. If you want to check the outgoing, you can do also the same. So we can call the outgoing attribute, and then we can do another loop. for the outgoing. So in this case, yeah, the outgoing of Busan is Daejeon. The outgoing of Daejeon, we have Busan, Incheon, okay, and so on. If I want to run the figure 14.3, so this is the function that I use to generate the figure 14.3. Okay. So I can call this function, and I would like to make this graph. So I can again call the incoming. So you can check with the graph that I show in the PowerPoint, and then I can also get the outgoing. There is another kind of graph, figure 14.14, and in this figure, we want to specify the element of the airport with the mileage. So you know, if you travel with the airplane, you will get some mileage. So we can specify in the graph. Suppose I want to travel from Boston to San Francisco, so you will get this kind of mileage. If you travel from Boston to Miami, you will get this mileage. So you can specify this element. Again, I will use the X list. So this element will be available in a tuple. So we can specify U, V, and this is the X. X is the element of the S. And you can see all the properties enter in this tuple. And then after you define of every of these X, you can create it. And again, you can check what is the incoming. And you can check what is the outgoing. Okay. Okay. Any questions? Okay, I think this is not that difficult. Okay. So let's move on the next section, which is about DFS, depth process. We are going to discuss depth process or DFS and how we can understand the DFS, the step-by-step of the DFS, and then we will look at some properties of the DFS, how we can find the path and how we can find the cycle. So DFS is the depth first search, and we need to understand some key point before we learn about the algorithm. Subgraph. What is subgraph? A subgraph of a graph G is a graph such that the vertices of S are a subset of the vertices of G. Okay, it means in a mathematical way, S is the subset of G. And then the edges of S are a subset of the edges of G. Means this one is the vertex. Okay, the vertex of S will be the vertex, the subset of vertex of G. And then we can also define, let's say this is the edge. The edge of S is the subset of G. Okay. So for example, we have a graph. Okay, this is a graph, and the blue color is the subgraph. So the original graph is like this one. Okay, the original graph is this one. And then you can see the blue color is subgraph because this node is the subset from all the nodes, and then the edges of S is also the subset. So this line is the subset from this big graph. There might be another concept, we call it spanning subgraph. So spanning subgraph is a subgraph that contains all the vertices of G. So if all the vertices of G is in the subgraph, then we call it, this is a spanning subgraph. We need to understand that a graph is a connected graph. So we call this is a graph is connected if there is a path between every pair of the vertices. Okay, you still remember path? Okay, we have the simple path and we have the path that is not simple. It means if I want to go from this node to this node, then there should be available paths. If I want to go from this node to this node, then there should be a path. Okay. If every node has path, then it is a connected graph. So this one is non-connected graph because you cannot go from this node to this node. So we call this is non-connected graph. And we call this is non-connected graph with two connected components because we have one connected component and we have two. So a connected component of a graph G is a maximal connected subgraph of G. So I can say that this is a subgraph of G. This is also another subgraph of G. So that's why we call this is connected components. So this is the first connected component, and then this is the second connected component. Last time you learned about tree. In the graph, you can also have the concept about tree. Or yeah, sometimes people say as the F tree or free. We call this tree as the forest tree. So the free, sometimes it refers to the forest tree. What does it mean? Yeah. So you can imagine tree in the forest. So in the forest there might be a lot of tree, and yeah, in the graph it's also possible. So the tree is an undirected graph T. Okay. So T means kind of variable to indicate the tree in undirected graph. So we call this is a tree in undirected graph if T is connected. So this is connected. And then T has no cycles. So there is no cycles like this. If no cycles, then yeah, we call this is tree. So please note that this definition of tree is different from the one of a rooted tree. You still remember rooted tree? When we learn about the binary tree, we have the root and then we have the internal node. We have the external node. Okay? We call this is rooted tree because the tree has a root. And then the tree has the internal node and then the tree has external node. We call this is rooted tree. But the tree in the graph is different. Okay. We can have another kind of concept, we call it forest. Okay. So forest is an undirected graph without cycles. So the connected components of a forest are trees. So we call this is a forest, and then the forest contain of several connected components. This is a connected component. This is a connected component, and this is just a single node. So it is a forest because it is a collection of trees. And I think some of you would like to do the team project with some basic algorithm like Kruskal algorithm, Prism algorithm, and those algorithms actually the basic of the spanning tree. So we call this is a spanning tree. And let's see what is spanning tree and what is spanning forest. A spanning tree is a spanning tree of a connected graph. Okay. So we call this is a connected graph because there will be non-connected graph. A spanning tree of connected graph is a spanning subgraph that is a tree. We can say that this is a spanning tree of this graph. We can also have this one as a spanning tree of this graph. We can also say that this is a spanning tree if we remove this x. Okay. And this spanning tree is not unique unless the graph is a tree. This graph is not true. So if we have the spanning tree, this one, every of this is connected. Okay. Okay. Every of this node is connected. This is okay. Every of this node is connected. Okay. So as long as it is connected, then we can say it is a spanning tree. So spanning trees have application to design of the communication networks. Yeah, if you know, in our school we have the Wi-Fi. Okay? So the Wi-Fi node actually it is also a kind of the spanning tree. We can connect one node of the Wi-Fi to another node of the Wi-Fi, and it should be a connection or should be connected. We can have a spanning forest of a graph. It is a spanning subgraph that is a forest. So the forest means a collection of trees. So some of them might be non-connected graph. So we can see from this concept, okay, we are going to learn about this depth first search. So the depth first search is a general technique for traversing a graph. You know, traversing. If you look at the concept of tree, okay, in the rooted tree, do you still remember in order traversal? Do you still remember pre-order traversal? Do you still remember post-order traversal? Okay, so those concepts are how we can travel in every node in the structured way. So that's for the rooted tree. But for the graph, we have another way. We call it, this is one of the general technique is the depth first search. So this is for the traversal in the graph. Okay. So DFS traversal of a graph it is to visit all the vertices and edges. And then it determines whether G is connected, and then computes the connected component of G, and then computes a spanning forest of G. As you know, in the algorithm and the data structure, we always consider the big O. Okay. The big O means the performance of the algorithm. We will look at the details. So the DFS on a graph with n vertices and m edges, it takes On plus m. So DFS can be further extended to solve other graph problems. For example, find and report a path between two given vertices. So we can use DFS for shortest path. We can use DFS to find a path. We can use DFS also to find cycle. So do you know what is the difference between path and cycle? A path is a travel from one node to another node, and the node will be different. Okay, so if it is a path, U and V is different, but a cycle is U and V is the same. So we want to go back to the origin, or we want to go back to the first one. So using DFS, yeah, we can do the cycle. Using DFS, we can also find the path. The depth first search is to graph what Euler tour is to binary tree. If you still remember, in the binary trees, we have one of the possible application, which is the Euler tour, where the Euler tour is the combination of the in-order traversal, pre-order traversal, and post-order traversal. Okay. Depth first can also do with this Euler tour. Let's have a break. Okay, I will continue after the break.